Right, hello again. We're going to look at pumpkins today. Seems a bit bizarre, but you'll see why. So some questions first of all, um, and pause it after I've read them to you. So, is it a source or sink? When I say pumpkin, I'm talking about the big fruit. Yeah, not so. This is a pumpkin plant. You can see its leaves, and there's a big fruit at the bottom. So, yeah, is the pumpkin fruit a source or a sink, and why? How did they evolve to be so big? And why are the seeds all genetically different? So have a pause and go over it. Could you answer those questions? Good, you're back. Brilliant. So sync. Well done if you actually paused it and thought it through. Because most people, trust me, will just keep on playing it, keep on playing it. But yeah, it's good to know that you know stuff. Anyway, yeah, it is a sink. The leaves are the source, or at least a mature leaf is a source because it's making more sugar than it's using. The fruit, however, is storing sugar. It's not making any sugar, therefore it's a sink. So hopefully your mass flow hypothesis knowledge of phloem is coming to bear there. Number two, how did they evolve to be so big? So this is a for mark answer. It says evolve, so it's a vibe question. And you always say there was variation in the population due to mutation. Therefore, some pumpkin plants had small pumpkins, some had big pumpkins. Yeah. And that variation was due to mutation. Those with big fruits were more likely to have more seeds, therefore they could have more offspring. Okay. Um, so again, it's a tricky one, but yeah, bigger fruits had an advantage. You could say they were more easily seen by animals that were going to eat them, or yeah, stored more seeds. Yeah, therefore those seeds are more likely to survive, and therefore grow into adults and pass on their alleles to their offspring when they breed. Therefore, the frequency of the large fruit allele increases in the population. And why are all the seeds genetically different? Well, a seed is a product of a pollen grain meeting a ovule, an egg cell. Okay, so that process is random because a male will release lots of pollen, and you have to get male and female plants, their pumpkins. Um, so yeah, the male plant releases loads of pollen. The female plant has lots of egg cells inside its flowers, and therefore, yeah, there's random fertilization. Also, because it's the fusion of gametes, it's the gametes are all different as well due to crossing over between homologous chromosomes in prophase 1 of meiosis and independent segregation that takes place during metaphase of meiosis. Okay. So yeah, there's ways in which we get genetically different plants. So if we look inside a pumpkin, you can see the high number of seeds inside it. Okay, and that's why they're useful for what we're going to do with, because we get lots of data from one organism. So we're going to assume that we've got one male and one female. They've bred, so pollen from the male have fertilized the female, and then we're going to measure the length of seeds that we get. Okay, and a seed is an offspring. Yeah, it's the product of fertilization between male and female gametes. Okay, so it's like these in here are all the offspring of two parent plants. Okay, so this is what you're going to use. This is a picture of pumpkin seeds. I put them on graph paper to help a bit, and there's a scale bar at the top. You're not going to measure all of them, you're only going to measure 10, so don't panic too much, but you will need a ruler. So we're going to tackle these things, these words. So I want to measure to high resolution. I want accuracy. We need to address reliability. We need to check off kind of bias and what anomalies are. Okay, often people write in answers, why did you do this? So that it was accurate, reliable, and free of anomalies and didn't show any bias. Yeah, when each of those require a different step. Okay, so for high resolution, well, I'm going to give you a document where I think it's a Word document, but you can zoom in. Yeah, you can zoom and zoom and zoom and zoom. Yeah, so there's a scale bar at the top. Therefore, I would zoom in so you've got quite a high level of zoom. Measure the scale bar, then measure seeds. Apply the scale factor to it to get a really accurate measure of the length of the seed. I want us to measure to 0.1 of a millimeter resolution. Okay, so these little squares on this graph paper are 2 millimeters long. Okay, that's 2 millimeters as I get an email, sorry. That's 2 millimeters long, so we're going to zoom and zoom and zoom so that we can measure to 0.1 of a millimeter. So that's accuracy. That's not accuracy at all. That's resolution. Okay, accuracy is making sure that I get the true value. Okay, and therefore it's all about doing things carefully. I need to line my ruler up right at the bottom and measure right to the top. Yeah, a line from the bottom to the top, the maximum length of the seed, not the width of the seed. If I measured across there, that wouldn't be accurate. Yeah, so I'm going from the top to the bottom. I'll know if you're accurate because whatever you measure should agree with what everybody else is. So you're all going to measure seed number 10. Okay, and I will gather your data for seed number 10 to see if you've done it accurately. Okay, so that's accuracy. Yeah, is doing things carefully. Use your ruler carefully. Yeah, line it up, zoom in nice and large. Yeah, do things carefully. What was the next word? Reliability. Okay, this is that well, if I wanted the mean pumpkin length, then I wouldn't just measure 3 pumpkin seeds. Okay, you would measure as many as possible. The more you measure, the more reliable your mean becomes. So we're not going to do means today. You aren't going to be doing means on Friday or some other data. But so reliability, you can kind of ignore it because we're not going to work out a mean. Gone the wrong way again. Bias. So you're going to measure 10 of these seeds. So again, I'm going to ask on a form, how did you do that? How did you select 10 seeds randomly? Okay, and then we'll go through on Friday which were the good ways and which were the less good ways. Okay, so yeah, you're going to select 10 that are free of bias. Anomalies. Now I've sorted this for you. I've not put any anomalous seeds on the picture. Yeah. Here's a little small one, number 14. In fact, number 6 is quite thin and small. Yeah. That's not an anomaly. That's just a small seed. Yeah. 22 looks like a chunky one. Yeah. It's not an anomaly. It's just a large seed. Okay. So an anomaly would be, maybe a seed was damaged and it was just half a seed. That would be an anomaly. Yeah, it would be an unexpected result that's not representative of the rest of the population. Yeah, so and I've not put any damaged seeds on the diagram. So anomalies are really, really awkward in biology because it's not always an outlier. Yeah, this I can still call number 22 an outlier. Yeah, it's quite large compared to the rest of them. However, it's not an anomaly. Okay. An anomaly would be due to some kind of error. Yeah, and that's why we repeat. If you do an experiment in chemistry where you're trying to, measure the volume of gas or something from a reaction, yeah, you do it, do it once, do it again, do it a third time to see if there's any anomalies present. Okay, because you might not put the bung on correctly, etc. There could have been a procedural error that led to the anomaly. So yeah, we need to be careful with the word anomaly. Because it's not always an anomaly if you're just a small seed. If we're measuring 6 former height and there was quite a short 6 former, you wouldn't say, oh no, I'm not going to measure you, you're an anomaly. You'd just be a smaller 6 former. So yeah, so we've tackled those 5. So you need to download the picture. Again, I know some of you haven't got laptops and you're working on smartphones, but you'll be able to zoom in and measure it. Just make sure that when you're zooming in, you don't. You need to zoom in to the same extent as the actual bar. So it might be tricky, but we'll have to just do our best. Tricky times, we'll have to do our best. So what you're going to write down, I've kind of started for you. So first of all, the task. You're going to randomly select 10 seeds from the picture. Okay. You're going to measure their maximum length using the scale bar, and you're going to measure to a resolution of plus or minus 0.1 millimeters. So you're going to be super accurate. Your ruler will only have millimeter markings, but because we're going to zoom in and use the scale bar, the answer that you get can be to a higher level of resolution because we're using a zooming in method. You need to make a copy of the results table. So you need to pull this. Sorry, it hasn't photocopied brilliantly. Photograph brilliantly. So we're going to look at pumpkin seed length distribution. See how I've put my seed lengths here: 8, 2, less than 9, 9, 2, less than 10. And because we're measuring to 0.1 of a millimeter, that's why it says 8.0 to less than 9.0. Okay. I've already measured all of these seeds. Okay, you're going to add your data, your 10, to this already. I didn't want to make it too mundane for you. I enjoy doing this kind of stuff. You know, I enjoy measuring seeds. It's almost my hobby. So yeah, so I've decided on these categories. So you're going to add your data to it and then pop down a total. Okay. We lack graph paper. That's why I'm making it simple. So we're then just on the paper below it. So we've done 3. Make a copy of the table and add your data to it. 4. We're going to draw a histogram. Remember, they have a linear x-axis. So see how my x-axis is going 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I haven't labelled it yet, but this is the seed length in millimeters. This is the number of seeds or frequency. We've got equal divisions, so it's not a frequency density thing. This is just a frequency histogram. I've kind of plotted my data, but yours will change. So, and I've got up in 2s on here, so I'm just using the lines on the page to go up in 2s. Do the same on your line paper. You must have some line paper. I've made a centimetre a division, and then I'm just plotting. Well, first one goes to 1, so I've gone across. Here you can see my ruler. I'm between 11 and 12. 11 and 12. I've got 11 so far, so I'm plotting 11. So I've gone to 11 here. I've drawn up from that line. I'm going across a centimetre, 10 millimeters, and then I'll come down to 12, and then I will construct a histogram. You need to know what histograms are and how to construct them. So that's why we're doing this. You're then going to take the midpoint at the top of each bar and draw a smooth line through these points to form a distribution curve. Okay, so currently I've got none between 8 and 9, so I will put a little cross where my pointer is, exactly where the point of the pointer is. I'd then do the same here between 9 and 10, same here between 10 and 11, same here, and then I would draw a smooth line. So it's a line that kind of goes through those central points, and we should get what's called a bell-shaped curve, a distribution curve, and that's what the next task is all about, where we're going to look at how distribution curves can actually change. Okay, so it's a bit, if we're in class, we'd be, each measuring a few seeds, entering it onto the computer, getting the class data, and then you'd be drawing histograms anyway. So we are doing the same as we would normally do, except I'd be coming around saying, no, you need to make sure that all these bars touch. It's a histogram. It has to be a linear scale. If it was a bar chart, we'd have stuff like, eye color, and it'd be brown space, blue space, green, and then there'd be frequency data here. So hopefully that makes sense. Good luck. Again, if you're trying to work it on a phone, be very careful of the zoom in, because when you zoom in, you then need to move to the scale bar and then move back to the seed that you've chosen randomly without changing the zoom. So hopefully that's doable. If not, do the best you can. It's not something I'm going to check. Or also, you need to check that seed. Which one did I pick? Number 10. Yeah. So one of your 10 must be number 10, and make a note of that somewhere, because I'm going to get you to write that down on the form so that I can check if you're measuring accurately, and also check if you're doing the work. Again, I'm speaking to the converted here, but I keep having to send emails every day to people who aren't doing the work. It's getting a bit annoying. Anyway, nice to speak to you, and I will sign off there.